Hello, today I'm going to sketch the function f of x equals 6x to the 1/3 plus 3x to the 4/3. This is of course equal to 3x to the 1/3 factored out in front of a 2 plus x. I like to do that initially because then it allows me to set this equal to 0 so I can find places where I have x-intercepts, right? There's two clear x-intercepts at 0 and at -2. So if I make a number line and I put on that number line the numbers -2 and 0, I can tell that this is see, that's a first degree, this part's a first degree, and so the number line would be plus, minus, and plus. So already I have information about where the graph equals 0, which is at -2, and it's 0, and I know it's going to somehow be below the graph here, or below the axis here, and above less than -2, and it'll be above from 0 on. That looks like a 1. Let me change that so it looks more clearly like a 2. Okay, first step would be to take the derivative and set it equal to 0 as well, since we are given the derivative. So if I set the derivative equal to 0, I can then find what are called the critical points, or the critical numbers. The critical numbers are where the derivative is either equal to 0 or is undefined. So looks like from the numerator we have a critical number occurring at x equals -1/2, and we have another critical number that is occurring where the derivative is undefined, which should be at x equals 0. So I will here make another number line, and on that number line, let's call it the f prime line, I need to label the numbers -1/2 and 0. So there's -1/2, there's 0, and again, first degree. Notice this time the x is being squared. That's a second degree, so that's a bouncer. So if we were to label our number line here, we would have positive, positive due to the bounce, and then negative. So the function will be decreasing, and then increasing, and then increasing. Next, we would take a second derivative, and we can see that the second derivative has been performed for us already and factored. So now I could make a second derivative line. So take a second derivative line, and where does our second derivative equal to 0? So I can determine where we're changing from positive to negative potentially, is I can see that there's an important point at x equals 1. So put that there at x equals 1, and 0 is still an important point because there is something going on in the denominator causing the f double prime to be undefined. So 0 is an important number. This time the multiplicities are odd, right? X minus 1 is raised to the first, and x is being raised to the third. These are both odd, so this time our number line would be a positive minus positive. So what this does for us is it tells us what the shape is going to look like in these different regions, right? See, there's a region, there's a region, there's a region through all these places on the f prime line and the f double prime line. So over here to the far left, we can see that we are decreasing concave up. From -1/2 to 0, we are increasing concave up. From 0 to 1, we're increasing but concave down this time. And over here on the far right, we would be increasing concave up. So as I draw my graph, I know that there is a change in direction that occurs at -1/2. So let me plot a number at -1/2. I know this is going to be below the axis because remember my initial part told me that the region between -2 and 0 was negative. From -infinity to -1/2, I need to be decreasing concave up, and I have to go through the 0. Then between -1/2 and 0, I need to be increasing concave up. So I'll draw something that looks sort of like that. Then from 0 to 1, I need to be increasing concave down. So I'll put a shape that looks something like that. And finally, for the rest of time, I will be increasing and concave up. So that's how we can use the first and the second derivative to create the graph of a function.